What if there's a future where all the oil companies are bankrupt? Without world hunger and energy shortages, there would be no need for war. Is this possible with the help of reinforcement learning AI innovations in the field of nuclear fusion? I'd like to be optimistic about this AI, but there are a lot of varied opinions. Let's take a look at some papers on this topic and see what's going on. This is a tokamak nuclear fusion reactor. In fact, it's the largest one in the United States. It holds the promise of limitless energy without greenhouse gases or nuclear waste. Imagine you're a machine learning engineer from General Atomics inside the D3D fusion facility working on experiments in this state-of-the-art tool. Ever since the National Ignition Facility proved experimentally that nuclear fusion could produce more energy than what is required to run the reactor, you've been unable to sleep because nuclear fusion just won't leave your brain alone at night. So you go to work. You might as well be productive, right? From a computer, you watch as superheated plasma forms a donut inside a simulated magnetic chamber. It only lasts for a few seconds, but it's progress. With a few more configurations of the algorithm, you run it again. You're alone in the room, but you're nervous because you know the entire world could potentially be looking at your work. This is the world's largest science experiment. 35 nations in total are working on this all at the same time. It's almost like an entire room of very powerful people are watching over your shoulder while you code. You think to yourself, there's got to be a way to improve on all of the recent breakthroughs that have happened and make this thing work for humanity. You stare at the simulation. The plasma blanket in the tokamak is in good confinement and control. You see, plasma that hot can do weird, chaotic things. It's called tearing instability, and it's why nations all over the world have trouble with the engineering of this problem. But this algorithm is supposed to fix that. It's so quiet at 4 a.m. You can hear your heartbeat in your chest. All you can do is stare at the purple light of the simulator, mesmerized. You're doing it. This algorithm is containing the reaction, controlling the plasma inside the reactor. You start to feel your excitement build. But all of a sudden, the program shuts down and the purple light goes out. Your heart sinks. It's only been a few seconds. The only thing left to do now is look at the code again, line by line, and start over. This is the energy of the stars. The sun and other stars create energy by fusing hydrogen into helium. And you get to be part of the team that's trying to bottle this star energy and use it here on Earth. That's so exciting. Okay, so how this works is the sun fuses hydrogen in its core, which is about 15 million degrees Kelvin. What kind of bottle are you going to put that in? A magnetic one, it turns out. So hydrogen is heated up, really hot, causes the molecules to move around, and that causes kinetic energy. You heat it up enough and that turns into plasma. Plasma is basically just like a magnetically charged cloud, and it's gonna end up spinning around in this reactor. They run a huge electromagnetic generator around the walls of this reactor to keep the hydrogen from touching it, because hot plasma touching the walls, that's bad, that causes damage. You're gonna heat this plasma hotter and hotter until it's between 100 million and 300 million Kelvin. Careful listeners will notice that I just said we're heating this to 10 times or hotter the temperature of the core of the sun. Why? There's a longer particle physics version of this answer that involves hydrogen atoms in the sun doing this thing called quantum tunneling. Go ask a particle physicist to explain this to you. I'm not going to pretend like I understand it, but I can give you the shorter math version of this answer. So the sun fuses hydrogen with hydrogen, which is actually not a very efficient reaction. There's a high probability of them forming helium-2, which is unstable, and it'll just break apart into hydrogen again. But with a lower probability, they can actually form deuterium, which is actually known as hydrogen-2. I don't know what the exact probabilities are, so let's just do what any good YouTuber would do and let's make some shit up for a second. Let's say that there is a 99% probability that these two hydrogens will fuse and form helium-2 and then just break apart into hydrogen again. That would leave a 1% probability that they would fuse into deuterium, also known as hydrogen-2. Now, the sun is big. After consulting my physics textbook, there are this many hydrogen molecules in the sun. So if all of those pair up and fuse at the same time, that leaves this many deuterium atoms if only 1% of those fusion reactions become deuterium. Because of the sun's size, low probability doesn't matter that much. We're on Earth, we don't really have that same luxury. Lucky for us, deuterium is pretty abundant on Earth. You can basically scoop it out of the oceans. When deuterium in the ocean combines with oxygen, it's called heavy water. That means we don't have to make it from scratch like the sun does. Fusing deuterium with deuterium yields a molecule called high energy helium-4, which is unstable, and there are a number of ways it can break down. You could get helium-3 and a high energy neutron, which produces energy, or you could get tritium, aka hydrogen-3, and ordinary hydrogen, or you could get a stable helium-4 molecule and a gamma ray. We want to be able to predict our results, so there is a different fusion reaction that we use more commonly for nuclear fusion here on Earth. We use the one where we slam a deuterium molecule into a tritium molecule. This makes helium-4 and a spare neutron, which is where the heat comes from. This reaction would create 17.6 mega electron volts of electricity. For this reaction, you need the plasma to be heated to 100 million Kelvin. If you're heating something that hot, you get some chaotic stuff mathematically. Particles don't behave like they're supposed to when they're that hot. And if that plasma touches the walls of the tokamak reactor, that's gonna damage stuff. So you heard me say that it does chaotic stuff. Chaos theory is the math of fractals. By definition, it's hard to predict fractal behavior. But this AI algorithm with reinforcement learning has done a pretty good job of doing just that. So that said, let's get back into this and learn more about it. You look at the time on your laptop and it's 3 a.m. again. Your most productive time of day! And like clockwork, the ideas start flowing again. By now, a whole team of nerds just like you also can't sleep because they have dreams of tokamak reactors. You're awake and working on it together in group chat. What if we stack this reinforcement learning algorithm on top of a neural net? Someone asks in the chat. Everyone starts feverishly typing, trying to figure that out. The weights of the neural net can be adjusted later to optimize the length of the time for a stable fusion reaction. Right now, we just need to build the framework out. The reinforcement algorithm will optimize based on the neural network, and then the model will gradually learn based on reward functions. Basically, it'll be like the algorithm is playing a game and trying to win as many rewards as possible. And that's how it'll be trained to keep the probability of tearing as low as possible. By this point, I imagine the real team of engineers has a name that they call themselves. So we'll give our hypothetical team a name as well. We're the Algorithm Alchemists, or AA for short. Cheers. You and the other members of AA need to control the tokamak reactor to guide the plasma along a narrow path where the pressure is the highest so that the stability is not exceeded. Team AA has essentially turned this into an obstacle avoidance problem where an obstacle has a high probability of causing the fusion reaction to stop. It's like trying to train a Roomba to turn around before hitting the wall instead of afterward. Okay, the algorithm's done. Let's run it. Team AA watches the simulation run. Excitement builds as the algorithm works, and it keeps working for seconds at a time that seem like hours, but it breaks at 5.5 seconds. A big instability was impossible to avoid, and it caused the fusion reaction to break down. The algorithm was able to forecast the instability 300 milliseconds before it occurred, but the beam had already reached its prescribed lower limit. It couldn't avoid it. Well, I didn't see that coming, someone said in the chat. But the algorithm did, someone else says. Machine learning humor. What if we weren't so conservative with the limits? You type into the chat box. We were conservative with the limits to make sure that the tokamak wasn't damaged, another member types. Okay, let's try a more moderate threshold, a third member says. You make some quick adjustments and you run the simulation again. Will this cause the fusion reaction to hold steady and avoid obstacles, or will it hit the wall of the tokamak reactor and damage infrastructure? This paper and algorithm is a proof of concept, but in my opinion, it's actually very promising work. I've read the paper very thoroughly. Now, I'm not a nuclear engineer, and I would appreciate hearing the opinion of a nuclear engineer who has read the same set of papers. As a machine learning engineer, I think this could work if we could get enough funding to nuclear fusion as a field. So let's talk about the funding and business prospects of this. The funding exists for projects that we're willing to pay for, but in this particular case, it's a little bit more complicated, of course. Tritium is radioactive and will decay into helium-3 in 12.3 years through beta decay, so it's not so abundant. The limited amount of tritium we do have is a byproduct of nuclear fission reactions. We definitely do not have enough tritium to power the entire world for nuclear fusion. We're short by like a lot. But what if we could make some? I see that we can slam a neutron into a lithium atom, like so, and then break it apart into tritium and helium. Now, we use lithium for a lot of things that we also badly need. And without lithium, all the information I told you in this video is basically completely worthless. Lucky for you though, I have another whole video where I discuss another new revolutionary AI innovation that when you couple it with a quantum computer, it could potentially decrease our demand for lithium by a lot and free up enough lithium that we could smack it with neutrons and make it into tritium so that we can use it for this. Click here to view the video and see if you think that that's realistic or not. Okay, bye.